Welcome to Unit 8 of Chemistry, Stoichiometry. What exactly is stoichiometry? Well, stoichiometry is the quantitative analysis of substances in chemical reactions. So we're going to combine our understanding of chemical reactions from the previous unit and our understanding of moles to explain how quantities of substances are converted during a chemical change. Stoichiometry comes from the Greek words stoichein, which means element, and metron, which means measure. So we're going to be measuring the amount of elements. So chemists use stoichiometry as a way to measure and compare reactants and products in a chemical reaction. How exactly do we compare the quantities of reactants and products? Well, stoichiometry compares the moles of the reactants to the moles of the products in a balanced equation. And since the mole is a standard counting unit for all substances, it can be used to compare one substance to another. So it's very difficult to compare the mass or volume of one substance with the mass or volume of another substance. And you know that the mole is a standardized unit that can help us to compare substances. So stoichiometry simply involves converting whatever units we're given, mass, volume, something like that, into moles, and comparing the moles of this substance with the moles of the product. So this would look like the mass of substance A, which is a reactant, we're going to convert into moles of substance A, and then we're going to compare that with the moles of the product B, and convert that then from moles into mass for product B. So this allows us to focus on the number of atoms by looking at moles and comparing moles here, instead of comparing the mass of one substance with the mass of another, which gets kind of confusing because sometimes we're discussing elements, sometimes we're discussing compounds, and there are numerous reactants and products sometimes in a chemical reaction, so it can be kind of complicated to compare these original values. The coefficients represent the relationship between moles of reactants and moles of products. And coefficients in a balanced chemical equation, remember, are the large numbers in front of the chemical formula. These coefficients can be used to create a mole ratio relating any two substances in a balanced chemical reaction. Let's look at an example here. We have 1 mole of nitrogen gas plus 3 moles of hydrogen gas yields 2 moles of ammonia. And here are our particle diagrams. We can see that our mass is conserved here. We have 2 atoms of nitrogen on this side and 2 atoms of nitrogen on this side, 6 atoms of hydrogen on this side and 6 on this side. So our equation is balanced. And these coefficients can be used to make the mole ratios. So we compare 2 substances at a time. We're not going to be able to compare all 3 of these at the same time, but we can compare any 2 in the reaction. So when comparing nitrogen gas to ammonia, the mole ratio would be 1 mole, using this coefficient here, 1 mole of nitrogen gas over 2 moles of ammonia, or sometimes we need the conversion factor to work in the opposite direction. So we could also write that as 2 moles of ammonia over 1 mole of nitrogen gas. So now is your turn. Practice writing the mole ratios comparing nitrogen gas and then hydrogen gas and ammonia. And remember that there are 2 ratios for each of these relationships. So you should have 2 different ways of comparing N2 and H2. Pause the video, figure those out, and then you can come back and check. So this should be your answer for N2 and H2, we can either have a 1:3 ratio or a 3:1 ratio, and we always write those units in there. If you are not in the habit of writing units, now is the time to start, or you're going to end up getting very confused as we work our way through this stoichiometry unit. So make sure that you are labeling these with moles of the correct substance. Make sure you're writing that substance on there. And then same here, 3 moles of hydrogen gas for every 2 moles of ammonia, or 2/3 in the opposite ratio. So how can mole ratios be used then? What's the point of doing this? Well, let's do a practice example here. How many moles of aluminum can be produced from 13.0 moles of aluminum oxide, which is Al2O3. So our first step is going to be write and balance the equation. So our equation here is going to be a decomposition reaction. We are breaking down aluminum oxide into aluminum and oxygen gas. And our equation is going to be balanced using these coefficients. And then we're going to use dimensional analysis and the mole ratio. So the way this works is we're going to take our given substance here, our given value, 13.0 moles. And again, we are writing that substance name here, 13.0 moles of aluminum oxide. And then we're using our mole ratio here. Since we have aluminum oxide on the top, we're going to put aluminum oxide on the bottom of this conversion factor. And from these coefficients, we know that there's 4 moles of aluminum for every 2 moles of aluminum oxide. And then we're going to cancel out those moles of aluminum oxide, leaving us with moles of aluminum. Multiply across the top, divide by the bottom, and we end up with 26.0 moles of aluminum. So how many moles of aluminum can be produced? 26.0 moles of aluminum. So that's how we use a mole ratio, just like a conversion factor in a dimensional analysis problem. So here's another one to practice. How many moles of hydrogen gas will be produced if 4.25 moles of potassium react with excess water? So for now, let's not worry about this excess water, or excess, I guess you're going to need the water, but don't worry about the excess part. How many moles of hydrogen gas will be produced if 4.25 moles of potassium react with water? So first we're going to create an equation for this reaction. We know that potassium is reacting with water, so those will be our reactants. One of our products is hydrogen gas, and the other product in this reaction is going to be potassium hydroxide. So using this equation, balance it so that we have the correct coefficients, and we can use those to make a mole ratio. So pause the video, balance the equation, and then come back. Okay, this should be your balanced equation with these coefficients. And now we are going to start with our given information, 4.25 moles of potassium, and use our mole ratio here, moles of potassium on the bottom, moles of hydrogen on the top, and we're going to multiply that out. Gives us 2.13 moles of hydrogen gas. It may be tempting for some of you to try to do this in your head based on some of these coefficients. I assure you that if you do not do the work the long way here and write out all of these steps, you are going to be totally lost as problems get a lot harder than this. So please take the time to write out the steps and practice using your dimensional analysis, or you're going to get very confused later on. And then just a note here about our excess water. That means that there is plenty of water in the reaction and it won't be a limiting reactant. You'll learn what that means later in this unit. But for now, just know that it's not going to stop this reaction. There's plenty of water to keep this reaction going until all of the potassium is used up. So in summary, stoichiometry uses the standard of moles to compare substances in a chemical reaction. The equation for the reaction must be balanced to create a mole ratio. So how do we convert from mass to moles? We know that we're going to need to do that because mass is not a standardized quantity that's going to allow us to compare substances. So how is molar mass used with mole ratios? It can be used in conjunction with mole ratios. These calculations can be used to determine how many moles of a product can be formed given the mass of a solid reactant. So if we have the mass of a certain reactant, or we can actually do this with products as well, but we'll start with a reactant just to make this simpler. If we have a known mass of a reactant, we can convert that to moles using the molar mass because we already know how to convert from mass to moles. So that involves using the molar mass. And then once we have the moles of whatever this reactant is, we can use the mole ratio to convert to moles of an unknown substance, which may be another reactant, could be a product, whatever the other substance is that we're trying to compare. And so this is the part that we use the mole ratio for. This is the part we use molar mass for of our known substance. So let's practice this one. How many moles of iodine gas will be produced from 12.5 grams of potassium iodide in the presence of excess chlorine gas? Again, don't worry too much about this excess right now. Just know that this reaction is going to keep going until the potassium iodide is used up. So how many moles of iodine gas, here's our iodine gas, will be produced from 12.5 grams of potassium iodide? So these are the two substances that we are comparing in this reaction. First step is to write our equation and balance it. So pause the video, balance the equation, and then come back. Okay, so you've balanced the equation and these should be your coefficients. Then we're going to convert grams of the known substance. Our known substance is potassium iodide. Since we have 12.5 grams of potassium iodide, that's our known substance from the problem. Convert that into moles using the molar mass. So we need to identify the molar mass of potassium iodide and then convert from grams of potassium iodide to moles of potassium iodide. The molar mass of potassium iodide is 166.02 grams. And now our third step is to compare the moles of the known substance, here potassium iodide, to the moles of the unknown using a mole ratio. The unknown substance that we want here is iodine gas. How many moles of iodine gas? So that's the one we're trying to get an answer for. So we're going to use a mole ratio to compare 1 mole of potassium iodide and then put the mole ratio here. Potassium iodide should be on the bottom and then iodine gas should be on the top, and use your coefficients to write a mole ratio here. So it should look like this. We had potassium iodide on the top, so we need it on the bottom. Using our coefficients from the balanced equation, we have 2 moles of potassium iodide for every 1 mole of iodine gas. Multiply all these across the top, divide by the ones on the bottom, and we end up with 0.03765 moles of iodine gas. And so that helps us to solve this problem. We are now at the units required by the question, so we are finished. This is not in correct sig figs yet, but our correct sig fig, since we have 3 up here for our measurement, would be 3 down here. 0.0377 would be our correct sig figs. We're not going to worry about our molar mass because this has more sig figs, and then these are our conversion factors. Those do not get factored into the sig figs because they are simply conversion units. What are the steps then for a mass to mass conversion? So we did this portion in the previous question. Now we're going to convert from moles of the unknown substance to mass of the unknown substance. So this is really a situation that you would use if you were doing experimental chemistry. This is the most practical. If we have a certain mass of a substance, how much of another substance could we make in a chemical reaction? Because often the purpose of a chemical reaction is to make a particular substance. And so sometimes we need a certain amount of that substance. We need to know how much of a reactant we need for that experiment in order to produce a particular amount of product. So our steps are going to be very similar with one final step that we didn't use in the previous question. So we're going to start by balancing an equation, and then we're going to convert from grams to moles using the molar mass of the known substance. Then we're going to use the mole ratio to convert moles of the known substance to moles of the unknown substance. And then our new step is going to be using the moles of the unknown substance to convert to grams of the unknown substance. And we're going to use the molar mass of whatever this unknown substance is in order to do that. So mass to moles, mole ratio, then moles to mass. So let's practice this. How many grams of iron 3 sulfide can be produced if 56.0 grams of iron are put into the reaction? And here's your equation. So we are starting with grams of iron. That's our known quantity. And we're trying to find grams of iron 3 sulfide. So that is our unknown. And we're going to start by balancing the equation. So pause the video, balance the equation, and then come back. Here is your balanced equation, coefficients for your balanced equation. And now we are going to start with our known quantity with mass, so grams of iron. And we're going to then use the molar mass of iron from the periodic table to convert to moles. Then here's your mole ratio of iron to iron 3 sulfide. And then use the molar mass of iron 3 sulfide to convert to grams of iron 3 sulfide. So if you can do that on your own, or you'd like to practice doing it on your own, pause the video. If you want to follow along, you can just keep going. Okay, so we're starting here with our mass. We go mass to moles by using the molar mass, and we've got grams on the top here, so we need grams on the bottom. And this is 55.845 grams of iron for 1 mole. That's from the periodic table. That's going to allow us to get rid of the grams. We are now at moles of iron, and we're going to use our mole ratio from the chemical equation up here. So 2 moles of iron, and we're comparing with 1 mole of iron sulfide, and we've got iron on the top here, so we need iron on the bottom. So we're going to put our 2 moles of iron from the equation on the bottom, and then we're going to put our 1 mole of iron sulfide on the top. That gets rid of our moles of iron. Now we have moles of iron sulfide, but we want to know how many grams of iron 3 sulfide can be produced. So we need to convert this moles value to grams. And in order to do that, we use the molar mass of iron 3 sulfide. So we're going to put 1 mole on the bottom, cancel those out, and use our molar mass on the top. Anytime you're using molar mass, you're going to put 1 mole on the opposite side of that conversion factor, because this is the number of grams per 1 mole. So we don't ever change this 1 when we're using our molar mass here. So 1 here, 1 here, and then these are going to change based on the equation. Do all of your multiplication and division, and you end up with 105.35 grams of iron 3 sulfide. So how is percent yield calculated? Well, the percent yield compares the theoretical yield, which is calculated using stoichiometry, just like we did the 105.35 grams of iron sulfide. This is our theoretical yield, what we should be able to get theoretically from this amount of iron. So this is our theoretical yield. And the percent yield compares the theoretical yield, which is calculated using stoichiometry, to the actual yield. So in a lab, what can actually be measured as far as number of grams. And so the theoretical yield is not always the value that we get in the actual lab, because there are a variety of additional reactions that might be happening that we're not accounting for, or there's procedural errors that may change the yield or the amount of the product that can be created. This comparison measures how successful the reaction was in forming the product. The higher the percent yield, the more successful the reaction was. So our percent yield is calculated by taking the actual yield, which is from the lab, the number of grams that were actually found in the lab, divided by the theoretical yield, which we calculated through stoichiometry, times 100. And you'll get some practice problems to do with that during this unit. So in summary, several steps are required to convert the mass of the known to the mass of the unknown using the molar masses and the mole ratio. This calculates the theoretical yield, which can be compared to the actual yield using the percent yield formula. So in some of the previous questions, I told you to ignore the in excess part of the question. Now we're going to get into why that's important. What is a limiting reactant? The limiting reactant is the reactant which runs out first during a chemical reaction. So it makes sense here, the terminology. A limiting reactant is one that is limiting the amount of product that can be made. So it's the reactant that determines the amount of product that can be formed. So let's use s'mores as an example here. What is the limiting reactant given these ingredients to make s'mores? So for a s'more, if this is our product, we need 2 graham crackers, 1 marshmallow, and 1 chocolate square. And we have 2 marshmallows, 3 chocolate squares, and 2 graham crackers. So what's the limiting reactant here? Well, our marshmallows here can make 2 s'mores. Our chocolate squares can make 3 s'mores. And our graham crackers, since we need 2 for each s'more, we can only make 1. Since these are all 3 reactants to make this one product, our limiting reactant is going to be the graham crackers, because we can only make 1 s'more out of that. So this is going to limit the amount of product that we can make. How is the limiting reactant determined? So we're going to do a mass to moles dimensional analysis calculation that compares each reactant to the product. So mass of the reactant to moles of the product using dimensional analysis. And the limiting reactant is the reactant that yields the smallest amount of product, the smallest number of moles of product that can be created, that's the one that's going to be your limiting reactant. So here, these marshmallows can make 2 s'mores, these can make 2 s'mores, these can make 1 s'more. So your limiting reactant is going to be the one that makes the least amount of product. But of course, when we're discussing chemistry, we're using moles and mass rather than number of items like we would in s'mores. So here's an example problem for you. Magnesium chloride is used as a supplement to treat magnesium deficiencies. If 6.85 grams of magnesium react with 8.55 grams of chlorine gas, how many moles of magnesium chloride will be formed? So as always with stoichiometry, we are going to start with a chemical equation and we're going to balance it. So this equation happens to be balanced already, so we can just put ones in for those coefficients. And so we're going to use both of these. We have 2 known quantities here. So we're going to use both of our known quantities, but we're going to do it individually. So 6.85 grams of magnesium is one of our reactants. And we're trying to figure out how many moles of magnesium chloride will be formed. So we're starting with one reactant and we're comparing it to the product. And then we're going to do the other reactant and compare it with the product. So starting with 6.85 grams of magnesium, do your stoichiometry conversions and determine how many moles of magnesium chloride can be made. Don't worry about the chlorine right now. We're just comparing magnesium to magnesium chloride. So pause the video, figure out how many moles of magnesium chloride can be formed. Okay, so we are going to use the molar mass here of magnesium. 24.305 grams per mole is the molar mass of magnesium, and that leaves us with moles of magnesium. We're going to use our mole ratio, 1:1 here. So 1 mole of magnesium on the bottom so that we can get rid of it over here. And then 1 mole of magnesium chloride on the top. And that is the unit that we want. We want moles of our product. So we're going to stop there and calculate by multiplying across the bottom, and then dividing those two numbers. 0.282 moles of magnesium chloride can be made from 6.85 grams of magnesium. So this is one reactant, and this is one amount of product that could be made based on how much magnesium we have. Now we're going to do the other reactant. So we're going to compare the chlorine to the magnesium chloride. So do the problem again, but use the chlorine and the chlorine ratio and molar mass instead of magnesium. So pause the video, do that, and then come back and check it. Okay, so we use the molar mass of Cl2 or chlorine gas, 70.906 grams per mole. And that allows us to cancel out the grams of chlorine, and we end up with 1 mole of chlorine gas using our mole ratio from the equation. We have 1 mole of chlorine gas for 1 mole of magnesium chloride. And when we calculate that out, we end up with 0.121 moles of magnesium chloride. So this amount of product is significantly smaller than this amount of product. So 8.55 grams of chlorine can only make this many moles of product, whereas 6.85 grams of magnesium can make more product. So the limiting reactant is going to be the chlorine, because this is the lesser amount of product. And so it's going to be limiting how much of the product can be made. So how then are excess reactants calculated? The excess reactant is going to be the one that's not used up, the opposite from the limiting reactant. Sometimes there's more than one excess reactant, but we calculate all of them in the same way. So the amount of excess reactant that remains can be calculated with these steps. So if we're looking at our excess reactant here, which is magnesium, we want to know how much is left over after we have formed this amount of magnesium chloride. So in a real lab, if you were combining these two amounts of ingredients or reactants, and you were only able to form this much of your product, you would have some of this magnesium left over since it's an excess reactant. So we want to know how much of it is going to be left over, because that can be theoretically wasteful in an industrial setting. So we want to be able to use as little of each of these reactants as possible. So let's find out how much is going to be left over. So the amount of excess reactant that remains can be calculated with these steps. Convert the lesser amount of product back to the original units for the excess reactant to see how much was used. So if we look back here, this is our lesser amount of product. We're going to convert that back to our original amount of the our original units of the excess reactant. So grams of magnesium is going to be our units of excess reactant. And then we're going to subtract that answer from the initial amount of reactant that's given in the problem. So there's a larger amount of the excess reactant given in the problem than what is actually used in the experiment. So that'll help us determine how much is remaining. So we're going to use the same question here and the same reactants and products. Now we're going to use the magnesium, which is the excess reactant, and we're going to see how much of that is left over. So starting with this lesser amount of moles, this was the amount of product that we could actually make because the other one was too high. There wasn't enough chlorine for that. So using this lesser amount of moles of product, we're going to work our way back to grams of magnesium. So you should be able to pause the video and do this on your own. Convert from moles of magnesium chloride back to grams of magnesium. So you'll need to use the mole ratio, and then you'll need to use the molar mass, and we're working in the opposite direction here. So your mole ratio is 1:1, and then we use the molar mass of magnesium to convert back to grams of magnesium, and we end up with 2.94 grams of magnesium were used to create this amount of product. And so only this amount was used, but we had 6.85 grams. So this is in excess, and we subtract to see how much is left over. So 6.85 from the question minus 2.94 grams used in the reaction gives us 3.91 grams of magnesium remaining. In summary, a limiting reactant is the reactant that forms the least amount of product. To calculate how much excess reactant remains, subtract the amount consumed from the initial amount of the reactant. So far, we've been talking about chemical reactions occurring in one direction, but that's actually not usually the case. Most reactions can occur in two directions, and we call that a reversible reaction. So many chemical reactions are reversible, meaning the newly formed products can act like reactants for the opposite reaction. Reversible reactions are written with a double arrow. So here's an example. Rather than having an arrow that only goes in one direction, we have a double arrow showing that it can move in either direction for this equation. When ammonium chloride is heated, it breaks down into ammonia and hydrogen chloride gas. When cooled, the ammonia and hydrogen chloride gas recombine to reform ammonium chloride. So these products can recombine to become reactants and then work that equation in the opposite direction. So that's a reversible reaction. When is a reaction at equilibrium? Well, chemical equilibrium occurs when the rate of the forward reaction is equal to the rate of the reverse reaction. And we can write that like this. Even though the rates are equal, the amounts of the reactants and products are often not equal in a chemical equilibrium. So the reaction might be occurring at a certain rate that is equal on both the forward end and the reverse end, but that doesn't necessarily mean that the amount of the products is equal to the amount of the reactants. In this scenario, the two sides of the bridge have a different number of people, but the rate at which they're traveling back and forth is the same. So we've got a small town over here, which may be a small amount of reactants, and we've got a big city over here, which could represent a large amount of product. It doesn't matter that these are two different sizes. What matters is that the traffic is moving at the same rate in between. So the reaction is occurring at the same rate forward and backward, even if the amounts are different. Because the rates are balanced but constantly in flux, the system is said to be in dynamic equilibrium. So this may be a term that you've heard in biology class, but dynamic means moving, and equilibrium, here we're talking about equal rates of reactions. And so it's kind of like being on a ball, balancing on a ball. You're constantly having to move, but you are able to stay balanced. But it's a constant shifting back and forth in order to maintain that level of balance. And this is the same dynamic nature as chemical equilibrium. How are moles relevant to chemical equilibrium? Well, the number of moles of a substance in a given volume is known as the substance's concentration. In equilibrium, the concentration of the products and the reactants become constant, not equal, but constant. So they stabilize. And the concentration of the products and reactants have stabilized over time in this graph. So if we start with no products and all reactants, and then as the reaction occurs, there are more products and fewer reactants until at some point they stabilize and you get the same rate for the forward direction as you do for the opposite reaction, the reverse reaction. And so the reaction here is in equilibrium. It does not necessarily mean that the concentrations of the products and the reactants are the same, that they are not necessarily equal, but the rates are equal and the concentration has stabilized. So it's not regularly changing, but it's a stable concentration, meaning that the product is being reformed and then reused at a constant rate. And so the concentration itself doesn't change. In summary, reversible reactions are written with a double arrow to show that they can occur in either direction. When the rates of the forward and reverse reactions are equal, the system is in chemical equilibrium. What is Le Chatelier's principle? So this has to do with equilibrium. Henri Louis Le Chatelier was a French chemist that studied chemical equilibrium. He devised what is now known as Le Chatelier's principle. When stress is applied to a system in chemical equilibrium, and generally we talk about that as being a chemical equation, the system will shift in a direction, forward or reverse, that relieves the stress and brings the system back into balance. So we're discussing here reversible reactions. And when something is changed in a reversible reaction that's in equilibrium, the reaction is going to shift so that either the forward direction of the reaction is going to be favored and it'll make more products, or the reverse reaction will be favored and will make more reactants. So when a certain stress is added to the equilibrium, it is going to shift to bring it back into balance, bring that reaction back into balance. And not necessarily here in balance, meaning that the amounts of products and reactants are the same, but that the rate is going to be equal so that they are able to be in equilibrium. So here, these students' weight was balanced. So picture this being a horizontal seesaw when they were first on it. And then a stressor was added. So a parent placed a backpack on this girl, and suddenly that stressor caused the seesaw to tip in her direction because this changed the equilibrium. And the seesaw then has to adjust to rebalance. So it is still balanced even at this angle. It doesn't have to be horizontal to be balanced, but it has shifted because of the addition of this stressor. So we're going to talk about different kinds of stressors that are added to chemical reactions and how they change those reversible reactions. So what factors can cause a shift in equilibrium? Well, there are three main factors that can shift a system in equilibrium. If the concentration, or moles in this case, of a reactant is increased, the reaction will shift to the right, or the product side. So this is going to be favoring the forward reaction. So here's an example. If we have two reactants here, A plus B, and we have two products, C and D, by adding more of A or B, the reaction is going to favor the forward reaction to rebalance the equilibrium. So in order to consume some of the excess reactant that we now have, the reaction is going to occur more often in this forward direction to get rid of some of that extra reactant. And that is going to rebalance the equilibrium, but it's going to have a greater forward reaction rate than it does reverse rate. So what factors can cause a shift in equilibrium? Well, there are three main factors that can shift a system in equilibrium. The first is concentration, and we've discussed that concentration is moles of a substance per unit of volume. Here we're just going to simplify it by discussing that concentration is synonymous here with moles. And that's not exactly true, but for our purposes, that's what we're going to use. So if the concentration or moles of a reactant is increased, the reaction will shift to the right, or the product side. So if we have two reactants here, A and B, and two products, C and D, if we add more of either A or B, these reactants are going to have a higher concentration. And there's going to be physically more molecules or particles of these reactants if we add concentration here. So they're going to be overcrowded. In order to use up those particles, the reaction is going to shift so that it favors the forward direction. It's going to start making more products. And so that's why we write this arrow in the forward direction. It's larger than in the reverse direction. If the concentration of a reactant is decreased, the reaction will shift to the left. So if we've got A, B here and C, D products, by decreasing either of these reactants, the reaction is then going to favor the reverse reaction to make more of them, to rebalance the equilibrium. So then our reverse arrow is going to be larger. If the concentration of a product is increased, the reaction will shift to the left. So again, just like in our concentration of reactants, if the product is increased, then there's going to be a crowding and excess of product, and then that's going to place stress on the equilibrium, and it's going to shift in the reverse direction. So here's a reaction showing that if we have C and D here, by adding more of either of those products, the reaction is going to shift to favor the reverse reaction to rebalance because there'll be more of these products. Likewise, if the concentration of a product is decreased, the reaction will shift to the right. So here, if we remove some of these, the forward reaction will be favored to make more of that product and rebalance. And this is used in industry. For example, ammonia is commercially produced for use as agricultural fertilizer. In the reaction, 3 moles of nitrogen gas plus 1 mole of hydrogen gas yields 2 moles of ammonia. Chemists will continually remove the ammonia and use that to sell. And this forces the reaction to proceed only in the forward direction, which forms more product and allows them to then create that product more efficiently and more of it for sale to the general consumer. So the second factor is pressure, and this only affects gases because they can be compressed, whereas liquids and solids cannot be. So by changing the pressure here, we can make the system seem more concentrated. By increasing the pressure, suddenly it seems like we have a greater concentration of particles. So if the pressure of a gas reaction is increased, the reaction will shift to the side that has fewer moles of gas. So here we are adding stress through pressure. If we're increasing pressure on that reaction, then all of the molecules of those gases are being concentrated into a smaller area. And so the reaction will shift to the side that has fewer moles because it has essentially a smaller concentration of particles. So looking at an example here, if these were all gases and we had 3 moles of gas in the reactant side and 2 moles of gas on the product side, and we increase the pressure of all of these, suddenly these would be more crowded because there are more particles on that side that has more moles, and so the pressure would cause the reaction to proceed more in the forward direction than in the reverse direction. If the pressure of a gas is decreased, then suddenly the number of particles is less crowded, and so the reaction will shift to the side that has more moles of the gas. So this would be an example of that. We're shifting to the side that has more moles. That's the reverse reaction being favored. If there are the same number of moles on both sides of the equation, the pressure will not affect the equilibrium at all. So here, by increasing the pressure of the gas in this chamber, the molecules are squeezed together, and that squeezing forces more molecules to move to the other side of the equation. So by increasing the pressure, it's going to shift to the other side of the equation, but we're definitely accounting for the number of moles in here. Temperature is our third factor. If the temperature is increased, the endothermic reaction is favored to absorb the extra heat. And if the temperature is decreased, the exothermic reaction is favored to release additional heat. So here we have an endothermic reaction where heat is going into the equation on the reactant side. So if we increase the temperature here, this is going to absorb extra heat. It's going to take in additional heat from that increased temperature, and it's going to favor this reaction in the forward direction. By decreasing the temperature, the reaction is going to try to produce more heat, and so it will be favoring the exothermic reaction. So if temperature is increased, then more heat is going to be absorbed, and so basically increasing the concentration of that heat and shifting this direction. If the temperature is decreased, then the reaction is going to try to produce more heat, and so the side that has heat on it is going to increase, and so that reaction is going to be favored in this format here, is going to be favored in the reverse direction. If the heat was on the other side, then the reaction would be favoring the forward direction, so it's favoring the side that the heat is on. In summary, according to Le Chatelier's principle, stress on a system in equilibrium will cause it to shift to favor either the forward or reverse reaction. Stressors can include changes in concentration of reactants or products, pressure, and temperature.